The most critical part of the Artemis I mission went wrong, and NASA's own models couldn't explain why. When the Orion spacecraft slammed back into Earth's atmosphere in December 2022, something happened that forced a multi-year delay for our return to the moon. It wasn't about budgets or politics, it was about physics pushing back, hard. What NASA discovered reveals the brutal truth about why we've been stuck in low Earth orbit for 50 years. So let's explore this together.
Heat shield failure.
Here's what's supposed to happen. When a spacecraft returns from the moon at 25,000 miles per hour, its heat shield, made of a material called avcoat, is designed to burn away, carrying the catastrophic heat with it. But what if it breaks apart in chunks? During Artemis I's re-entry, that's exactly what happened. In over 100 locations, pieces of the charged shield material flaked off in ways that years of computer modeling never predicted. This forced NASA into a year-long investigation, led by experts like Howard Hu, the Orion program manager, to figure out what went wrong. Here's the terrifying bottom line. The models failed because of the unique re-entry profile. Orion performed a skip entry, dipping into the atmosphere to slow down, then briefly skipping back out before the final descent. During that brief skip, gases built up inside the avcoat material, and without continuous heat to vent them, pressure mounted until it fractured parts of the shield. This single, unexpected failure of physics is a primary reason the first crewed mission, Artemis II, was pushed to April 2026 at the earliest. It was a sobering wake-up call that returning from the moon is far more dangerous than we remembered.
Radiation rivers.
Think it's just the heat that can kill you? Think again. What if the deadliest threat was completely invisible and could end a mission based on which way your ship was pointing? While everyone was focused on the heat shield, sensors aboard Artemis I made a chilling discovery. The Mare experiment, led by principal investigator Thomas Berger of the German Aerospace Center, placed 2 mannequins inside Orion to measure radiation exposure. The results were staggering. Data showed that simply by changing the orientation of the spacecraft, the radiation dose inside could be cut in half. Let that sink in. We're not talking about thicker shielding, we're talking about geometry. It's like discovering you can survive a hailstorm only if your car is angled just right. This matters now more than ever because we are currently at the peak of solar cycle 25. The sun is more active and violent than it has been in years, spewing solar flares and radiation. Flying through these invisible rivers of energy at the wrong angle could expose astronauts to life-threatening radiation levels, a risk NASA scientist Tony Slaba and his team are working to model and mitigate. This isn't a simple engineering problem, it's a dangerous balancing act where a few degrees of rotation could be the difference between a successful mission and a medical catastrophe.
Deadly dust.
The biggest nightmare on the moon might just be the ground beneath your feet. Forget gentle, soft dust. Lunar dust, or regolith, is a menace. It's composed of microscopic shards of glass and minerals, formed by billions of years of meteorite impacts. Unlike dust on Earth, it has never been weathered by wind or water, so every particle remains razor-sharp. Apollo 17 astronaut and geologist Harrison Schmitt learned this the hard way when he experienced what he called lunar hay fever. Sneezing, watery eyes, and a sore throat after tracking the dust inside the lunar module. Modern studies confirm his experience. This dust is toxic. Scientists like Kim Prisk, a pulmonary physiologist who has studied the effects for ESA, warn that these fine particles can lodge deep in the lungs, tearing tissue like microscopic knives. Because the moon has no atmosphere, the dust is also electrostatically charged by the sun, meaning it clings to everything. Spacesuit seals, visors, solar panels, and critical equipment. Researchers like Michaela Smith have shown that while it may be less chemically toxic than urban pollution, its abrasive nature presents a severe mechanical hazard. This isn't just an inconvenience, it's a relentless engineering challenge that threatens every aspect of a mission.
Gravity traps.
Imagine flying a spacecraft in a perfectly calculated orbit, only to feel an invisible hand pulling you off course. That's precisely what Apollo mission planners encountered. Their spacecraft would mysteriously dip in altitude or drift from their trajectory for no apparent reason. The cause? The moon's gravity is not uniform. In 1968, Paul Muller and William Sjogren at NASA's Jet Propulsion Laboratory discovered massive, dense concentrations of material buried beneath the lunar maria. They named these anomalies mascons, or mass concentrations. These mascons are so powerful they create gravitational traps, tugging on any object that passes over them. The Apollo 12 landing was nearly jeopardized by these anomalies, until engineers learned to account for their pull. For decades, their exact structure remained a mystery. It wasn't until NASA's Grail mission, led by principal investigator Maria Zuber, fully mapped the moon's gravity field in 2012, that we understood the scale of the problem. The map revealed a lumpy, uneven world where navigating a low orbit is like traversing an invisible obstacle course. These gravity wells make precise landings incredibly difficult and require constant course corrections, another hidden danger proving the moon is anything but a passive target.
The moon rings.
What if you could strike the moon and make it ring like a bell? That's not science fiction. It's exactly what Apollo astronauts discovered, and the discovery was deeply unsettling. The Apollo 12 crew deliberately crashed their ascent stage into the lunar surface. The resulting moonquake, monitored by seismometers placed on the surface, shocked everyone. On Earth, seismic waves dissipate quickly. But on the moon, the vibrations lasted for over 55 minutes. Gary Latham, the principal investigator for the Apollo seismic experiments, described it as the moon ringing like a bell. The reason is that the moon's interior is bone-dry and fractured, allowing seismic waves to travel with almost no dampening. A single impact can set the entire celestial body vibrating for an astonishingly long time. This revealed a world far different from our own, one that is geologically rigid and resonant. More recent analysis of the old Apollo data by scientists like Yoshio Nakamura confirmed another startling fact. The moon has a solid inner core, much like Earth. This finding supports the theory that the moon was born from a violent collision with a Mars-sized object in Earth. This raises a profound question. If the moon is our planet's broken twin, born in cosmic violence, what other secrets are locked inside its strangely resonant interior?
Forgotten data.
For 8 years, from 1969 to 1977, humanity listened to the heartbeat of the moon through the Apollo Lunar Surface Experiments Package, or ALSEP. This network of seismometers gave us our only direct data from the interior of another world. Then, in 1977, due to budget cuts, NASA sent a command from Earth and switched them all off. We have been deaf to the moon ever since. The loss is incalculable. Scientists like Yoshio Nakamura are still finding new discoveries by applying modern computing techniques to the old Apollo data, proving its value decades later. But what's even more shocking is what happened to the original footage of our first steps on the moon. In the 1980s, during a shortage of magnetic tapes, NASA erased the pristine, high-quality, slow-scan television tapes from the Apollo 11 mission to reuse them. The raw footage of one of humanity's greatest achievements was sacrificed to save a few dollars. Richard Nafzger, an engineer who led the search for the lost tapes, confirmed their fate in 2009. These events aren't just historical footnotes. They show a pattern of abandoning our most valuable extraterrestrial science, leaving a 50-year gap in our understanding of our closest celestial neighbor.
Soviet failures.
While America celebrated its victory in the space race, the Soviet Union was hiding one of the biggest engineering disasters in history. The Soviets were just as determined to reach the moon, and they built a rocket to do it, the N-1. Designed by the legendary chief designer Sergei Korolev, the N-1 was a monster, meant to rival the Saturn V, but it had a critical and ultimately fatal design flaw. While the Saturn V used 5 massive F-1 engines on its first stage, the Soviets couldn't build engines that powerful. Instead, their chief engine designer, Nikolai Kuznetsov, clustered 30 smaller engines at the base of the N-1. It was an incredibly complex system that had to work perfectly. It never did. All 4 unmanned test launches of the N-1 rocket between 1969 and 1972 ended in catastrophic failure. The second launch, on July 3, 1969, resulted in the largest artificial non-nuclear explosion in history, destroying the launch pad and nearly the entire launch complex. After Korolev's death, his successor, Vasily Mishin, oversaw the program's final failed attempts. The repeated disasters forced the Soviet Union to abandon its lunar ambitions completely, a secret they kept hidden for decades. The story of the N-1 is a stark reminder of just how difficult and deadly the journey to the moon truly is.
The long gap.
On December 14, 1972, Apollo 17 lifted off from the lunar surface. No human has been back since. Why? Well, the official answer points to shifting priorities and budget cuts. NASA Administrator Thomas O. Paine announced the cancellation of Apollo 20 in January 1970 to free up a Saturn V rocket for the Skylab space station. Apollos 18 and 19 were canceled later that year. The focus shifted to the space shuttle, and then the International Space Station, which, honestly, consumed NASA's budget for decades. But, there's a deeper story. In 2004, President George W. Bush announced the Constellation program, promising a return to the moon by 2020. After billions were spent, President Barack Obama canceled it in 2010. Apollo astronaut John Young believed one reason for the cancellations was NASA's fear of losing astronauts on such a risky endeavor. The truth is, the gap wasn't just about money or politics. It was about realizing just how razor-thin the margins of success truly were. The moon proved to be far more dangerous and technically demanding than the triumphant narrative of Apollo suggested. The 50-year silence isn't just a pause, it's a testament to the immense difficulty of what those first missions accomplished.
Artemis struggles.
If returning to the moon was easy, we would have done it decades ago. The Artemis program proves it's anything but. Rebuilding the capability to go to the moon from scratch is a staggering undertaking. The Space Launch System, or SLS rocket, took 17 years to develop. The Orion capsule's heat shield anomaly is still being addressed. According to NASA Associate Administrator Jim Free, the delays are necessary to ensure astronaut safety, with issues ranging from life support systems to launch abort batteries. But it doesn't stop there. The landing itself depends on hardware that hasn't flown yet. The new spacesuits being developed by Axiom Space haven't completed vacuum testing. And SpaceX's Lunar Starship, the vehicle designated to actually carry astronauts to the surface, has yet to perform an orbital refueling, a critical step that may require multiple launches for a single landing. Bill Nelson, the current NASA administrator, has had to officially push the timeline back, with Artemis II now scheduled for 2026 and the Artemis III landing no earlier than 2027. Each component of the Artemis architecture represents a monumental engineering challenge, and each one must work perfectly. The ongoing struggles show that even with 50 years of technological advancement, the moon remains a formidable objective.
Hostile environment.
The moon is not a welcoming place. It's a world of violent extremes that pushes human technology to its absolute limit. In direct sunlight, temperatures can soar to 250 degrees Fahrenheit, hot enough to boil water. Just a few feet away in shadow, it plummets to minus 250 degrees Fahrenheit. Planetary scientist David Kring, who has spent his career studying the moon, emphasizes that this environment is one of the most hostile in the solar system. Beyond the temperature swings, the moon lacks the protection of an atmosphere or a global magnetic field, leaving everything on its surface exposed to unfiltered solar radiation and micrometeorite impacts. But the hostility isn't just physical, it's psychological. Apollo astronauts reported moments of profound unease in the stark, silent, and utterly alien landscape. Standing in a world where nothing has ever lived, under a black sky, creates a sense of isolation that is hard to comprehend. When you combine these factors, the radiation, the killer dust, the gravity anomalies, the seismic ringing, and the extreme temperatures, you get a full picture. The moon isn't passively waiting for us. Its environment is actively fighting against human presence in every way imaginable. So, no, NASA didn't uncover a conspiracy. It uncovered something far more sobering: the raw, untamed hostility of space. The Artemis I mission served as a brutal reminder that the moon is not a solved problem. The heat shield failure, the radiation dangers, the abrasive dust, and the unpredictable gravity are not minor details. They are fundamental obstacles to survival. The greatest achievement of the Apollo program wasn't just getting to the moon in 1969, it was getting 6 crews back alive. What do you think is the biggest challenge we still need to overcome? Let us know in the comments below. Don't forget to like, subscribe, and hit the bell icon so you don't miss our next video exploring the future of the Artemis missions. Thanks for watching InnoVision Tech.